Okay, so let's do another example of hypothesis testing. We have a new question here. As you can see, here we're not given too much information. Well, we're given information, but it's very apparent that we're given data instead of the results from our sample, right? So instead of saying I went out and collected a sample, here's my sample mean and my standard deviation and my population, what have you, we are given sample data. So let's go ahead and read this, right? An employment information service claims that the mean annual salary for full-time female workers over age 25 and without a high school diploma is more than $18,500. The annual salaries for a random sample of 12 full-time female workers without a high school diploma are listed. At the alpha equals 0.1 or the 10% level, is there enough evidence to support the claim that the mean salary is more than $18,500? So this is taken from the Bureau of Labor and Statistics. We have a random sample of 15 here. So before we can really proceed any further, we have to kind of talk about what our data are telling us, right? So from the data, we know that the sample average is $19,086.50, and I have a standard deviation as such, 1417.7399. Okay, so it's good to stay as accurate as possible. I generally want to have at least 4 decimal places. That's my standard for this class, so that's what we're going to stay with. Okay, so now I can start to begin the hypothesis test. First thing I need to do is I need to figure out what my null and my alternative hypothesis are, right? So here it says that an employment information service has a claim, and their claim is that the annual salary for these group of people is more than $18,500. Okay, we gathered a sample, and it looks like our sample average is more, right? So default would be that it's 18,500 or less. We generally just need to put the equal sign. So my null hypothesis is that this population mean is 18,500 or less. We could just keep it as equaling 18,500. And my alternative is that it's actually more than that, right? So I have my null and my alternative. My null is that my population mean is 18,500 or less. I could put a less in here also, but we no longer have to do that. We can just put equals all the time for the null hypothesis, and this alternative that will have a greater than or less than sign, right? So I think it's more. If it's not more, I'm just saying it's equal. Okay. So after we find and state our null and alternative hypotheses, we need to talk about what kind of test we're doing, right? So I literally know pretty much nothing about the actual population, except for I'm assuming that the true population mean is 18,500. I have no idea about the standard deviation of the population. There's no information or records for me to figure that out unless I go to the U.S. Bureau of Labor Statistics and look that up. Maybe they have that there, but it's not given to me, right? So I also have a very small sample size. I have 12, okay? So I have a small sample size, and I don't know anything about the population except for this assumption that I'm making that the population mean is 18,500. So I need to use the t-distribution, the student's t-distribution. We do that when we have a small sample and we know nothing about the population, okay, the standard deviation. From my alternative hypothesis, I'm looking for things that are more than 18,500. I'm assuming that things are more than what's being stated, okay, especially coming from my data. My data kind of supports that a little bit. So the type of test I'm going to be doing is a more than means a right-tailed t-test of means. Okay, a right-tailed t-test for means is the type of test I'll be conducting. Next, we want to state the conditions for the central limit theorem. Again, I need to have these things present in order to conduct my test in the first place, right? So we'll start talking about the conditions necessary for the central limit theorem. Okay, so before we get into the distribution, or our conditions here, I'm sorry, we have to let the reader know that we're not using an actual normal distribution. We're going to be using the t-distribution, which is an approximation of the normal distribution. So I'm going to state to my reader that I'm using the t-distribution and that I have a certain number of degrees of freedom. Okay, the degrees of freedom is what tells me what my distribution looks like. Okay, what that curved bell graph looks like. If I have a small degree of freedom, it's going to look different than if I have a large degree of freedom. The larger my degrees of freedom, the more that my graph looks like the normal distribution. The less degrees of freedom, the less it looks like the normal distribution. Okay, but the t-distribution is basically used to approximate the normal distribution when we have not so optimal sort of conditions, right? So here I have 12 pieces of data. So my degrees of freedom is 12 minus 1, or 11. I have 11 degrees of freedom. Okay. So from here I want to start to detail why the different conditions for the central limit theorem are met. So I'm going to talk about my randomness, my independence, and why I am approximately normal, right? And which is because we're using the t-distribution. Okay. I know I have randomness because it says here that this is a random sample of 12 full-time female workers without a high school diploma, right? So I know I have randomness because it stated that the sample was randomly collected. Okay. Next I need independence. N equals 12 is a small sample from a large population. Remember, it's independent if my sample size is less than 10% of the population. So 12 is 10% of 120. I'm pretty sure that there is more than 120 full-time female workers that are over the age of 25 without a high school diploma in the United States, right? So this is a fairly good assumption that I can make here. Okay. The next thing is I need normality. And again, the t-distribution is basically an approximation to the normal distribution when we have no information regarding the population standard deviation, right? I only have the standard deviation for my sample. I want to tell them that I am using the t-distribution and it's robust. It's resistant to small samples, and again, I'm telling them at the beginning that I'm using the t-distribution. So since it's resistant to small samples, that's good enough for me to let them know that I basically have some normality in my graph. Okay. Next, we need to state the significance level that we're testing at. So as is stated above, we are at the alpha equals 0.1, which in terms of percentages is the same thing as 10%. Okay. So we will be testing at the alpha equals 10% level. The next thing that we have to do is start to talk about our graph. So for the first part of our graph, we want to talk about our test statistic. It's basically the t-score, since we're doing a t-distribution, a t-test, right? We don't have a z-score because we don't have the normal distribution, right, which uses z-scores. We have t-scores. And our t-score is calculated basically the same way that z-scores are calculated, except instead of using divided by the standard deviation for the population, I'm going to do the exact same thing but divide by the standard deviation for my sample because I don't have that information. Okay. So my test statistic is calculated by finding t of x bar, okay, my sample mean. The t-score for my sample mean is my sample mean minus what I'm assuming to be the population. So my sample minus my assumed population. And instead of sigma divided square root of n, you know, the population for the standard deviation for the population, I'm going to use the standard deviation from my sample. If I have a good sample, it should be pretty close in value, so this is an approximation to what I'm assuming my population is, right? Assuming I have a good sample. So if I find all this value, I get a t-score for my sample mean of 1.4331. Okay, that is my test statistic. That is the value I will be looking at in my graph of my t-distribution. Okay, so the next thing that I need is I need the t-score for my alpha level, for my 10% value. Okay, depending on what calculator you have, you can find this or you can't find this, right? So if you don't have a TI-84, your calculator is not going to do this for you. Okay, and you really just need to use the t-test option in your calculator to get the important information. If you have a TI-84, you can find the t-score by using inverse t for a certain area given under your graph. So my t-score is, for alpha is 10%, t of 0.1 is inverse t 1 minus 0.1. So this will be inverse t 0.9 and then 11. So my degrees of freedom is last and the area under my curve is first, right? So how come I'm not using 10%? Well, I'm doing a right tail. On the right side, I'm using up all of my stuff up until 90%, and then my tail will have the last 10%. So I need 1 minus 10%, or 90%, and then my degrees of freedom. And my critical value will be a value that is over on the right side of my graph. Okay, so let's go ahead and take a look at a graph and see what that looks like. Okay, maybe before that we look at our p-value. Okay, so we can talk about how to calculate our p-value just from these two given pieces of information. So when we look at our graph, we'll look at our test statistic, our critical value, and we can compare these things and see where they lie. Right? So even without looking at my graph, we can kind of tell whether or not my sample mean is too far away from what I'm thinking it's supposed to be or not, right? So basically, since I'm doing a right tail test, if my test value, if my sample value, my sample mean, or the test statistic for my sample mean is too far away from what I assume to be true, then I'm probably wrong about my assumption, right? So where's my cutoff value? How far is too far? My critical value is how far is too far. So 1.3634 is too far away. Mine is 1.4331. I am too far away. I'm past my critical value, or I'm past my cutoff value, right? So let's look at the p-value and we'll look at the graph. We'll kind of throw this all together at once. Okay, so just taking a look at how to calculate the p-value. It's the probability that I get other t-scores larger than the t-score that I got, assuming that my null hypothesis, 18,500, is true. To do that in the calculator, instead of normal CDF, it's t-CDF, or the t-distribution. I put in my value, the lowest, the highest, and the degrees of freedom, right? 11 degrees of freedom. So doing that, and I get out 0.0898, which is less than my value. So the probability is smaller than my cutoff probability, which makes sense with what I was saying. My test value, my sample mean, is farther away from my mean than my cutoff value. So what that means is that I'm probably wrong about my assumption, right? This is the probability that this happens given that this is true. If that probability is really small, smaller than my cutoff value, this is probably a wrong assumption. My null hypothesis is probably not true. So let's look at the graph of this, and we'll just kind of reiterate those 2 points. So let's remember our test statistic, 1.4331. Our critical value, 1.3634. It's less than, right? My cutoff is less than my my test value. And let's look at that area. Okay. So let's start off with our graph of the t-distribution with 11 degrees of freedom. And let's talk about our rejection region, right? So we're rejecting at the 10% level. Alpha is 10%. My critical value, or what I've been calling the T score of alpha, T of 0.1, on the right side, right? Not on the left side. So things that are larger than this. And that was a value of 1.3634. This was my cutoff value. Anything beyond this will lie in the rejection region, right? I'll be in the red. So if we look at our value that we got from our data, right? So we'll look at the t-score from our sample mean. You can see that that's the green, and I am inside of the red, just barely, right? I'm just barely making it. My test statistic, T of X bar, was 1.4331. It was further away from what I'm calling the center of my distribution, right? My mean, my population mean, my assumed population mean, than my cutoff value, right? My cutoff value is closer, my sample is further. I am inside of the rejection region, okay? So if I want to, you can swap the colors a little bit here, and you can see that I am inside of the red. I am not outside where everything is safe. I am in the rejection region. I'm going to conclude to reject my null hypothesis. The probability of this happening is too small. It's below my cutoff, right? So the probability of getting a t-score, the same as what I got, or even more extreme, given that what I'm assuming to be as true actually happened, is a very low probability. So the likelihood that I have a bad test sample, right, a bad sample mean, is unlikely. It's more likely that my assumption about the null hypothesis, that the mean is 18,500, is more likely to be wrong than the probability that I have a bad sample. That's basically what it's saying, right? That my assumption is more likely my assumption is false rather than I just happen to get a bad sample, right? This sample is so bad that it's more likely that my assumption is false. Okay, that's another way to think about it. Okay, so I'm in my rejection region. So this kind of breaks down 3 different ways. I can talk about me knowing that I'm not correct, right? One is that my p-value is small. It's smaller than my alpha. The other is that my test statistic is further away from my proposed population mean than my critical value, okay? Meaning that I'm landing in the rejection region, okay? So let's talk about how to summarize our conclusion. Okay, so back to our work. Again, my p-value is less than my significance level, or I can think about it as my test value that I got from my sample mean is further away than my cutoff. Okay, my sample mean is too far from my assumed population mean. Okay, this 19,000 is way far away from this 18,000, right? Taking into assumption what my standard deviation is, right? So I'm past my critical value. So what does this look like as far as our conclusion? Okay. Since my p-value is this thing, right, which is less than my alpha value, so I have this thing being less than this thing, right, we can conclude that I will reject my null hypothesis. It's more likely that me assuming that this is true is incorrect rather than me assuming that I just happen to have a bad data sample, okay, or bad sample data. So there's enough evidence to suggest that the mean salary for full-time female workers over age 25 and without a high school diploma is more than 18,500. I again need to state my conclusion. Not only what am I doing, I'm rejecting this null hypothesis, but what does that mean, right? I need to be able to talk about what that means in the context of my question, okay? So the next thing that we need to do is talk about our possible errors. We talk about conclusions, then we talk about things that maybe we got wrong. Okay, so to finish up the problem, I have a possible type 1 error, meaning that we concluded to reject the null hypothesis when in fact the null hypothesis was actually true. Okay, this is a possible error we could have made because my conclusion was to reject this original claim, right? And to assume that this alternative claim is true or more likely to be true, right? So maybe I made an error in judgment and it actually is true that the population mean is 18,500 for full-time female workers over age 25 without a high school diploma, right? So we want to state that. We conclude that the mean salary for full-time female workers over age 25 and without a high school diploma is more than 18,500, so that's what I did before, right? When it actually is not. So that's me being incorrect, right? I'm assuming that it is when maybe it isn't, right? So I'm assuming that this is not true when possibly it is actually true. And that's the possible error I made in my conclusion.